All right, hello everybody. So, got a quick video I wanted to do here about how to calibrate your SuperX detector. This is really easy to do. Basically, you need a standard to do this. So, I actually have an aluminum diffraction standard on a copper grid. So, it's a copper grid with a carbon film that has aluminum evaporated on it. And so we can use the copper peak and the aluminum peak, both the K alpha peaks, to calibrate the energy scale for the EDS. Okay, so let's open the column valves here. Okay, and I already have my monochromator centered. You can see I'm already at eccentric height, so you want to be there as well. Um, and then we need to make sure that we're actually, so right now we're not illuminating any part of the grid. If we go to Velox acquisition here and just do EDS, so we're seeing a little bit of a copper peak here, but not enough. So we need to actually move the stage till we actually see more of a copper signal here. Okay, so you don't have to do much. So I'm just like barely nicking the edge right there, as you can see down here, but I'm already getting a good. Yeah, so if you what you want, so this is aluminum K, this is your copper aluminum K alpha, copper K alpha. You want those about the same height, ideally. So I'm just bumping the stage here till I kind of get that. Yeah, so that's pretty close right here. Now, of course, it's using 4 detector segments. They all come at different angles, so it's probably not going to be quite the same for each of them, but we'll use this as a starting point. Okay, so we'll stop this. And then you want to open up Microscope Launcher. You don't have to be logged in as service to this. You should be able to do this in just normal mode. Click Tools and then SuperX G2 Calibration. Okay, then click Calibrate Detector. Select all segments. And then for peak 1, I don't think it matters which one is higher or low energy, but let's make this the low energy one. So we'll do aluminum, and it's already selecting K alpha there. And then for element or peak 2, let's do copper and K alpha peak. And then click OK. And then it's giving us this. So it wants us to make sure your detector is at a stable temperature and that we don't have too many counts. So I think we should still be okay, even if we're a little bit, well, it's not letting us. So it's not giving me okay. So I'm going to have to reduce this a little. So I'm going to change my beam here. See, now we're not hitting any part of the grid though. So now I'm actually translating the beam. I want this just at the upper end of that green region. There we go. Because that means I'm going to get enough. Not worried about getting an aluminum signal, but I want to make sure I get enough of the copper because that's going to calibrate the high. All right, that's good enough. So we'll click OK. It's going to do that each time for each segment. So this is only for the first segment. So I would say do this like every year, once a year. In my experience, it stays very stable. So you shouldn't have to do this more frequently than that. But since I had this sample in here, I wanted to show you how to do this. In principle, you could do this with any 2 peaks. You want the 2 peaks well separated though. Okay, so these are separated by about 7 EV. I mean, it'd be even better if we had something, I guess, that was kind of out here. Generally speaking, though, we usually don't detect X-rays beyond 20 keV. Although on this system we could go out to 40 keV. But yeah, you want some separation here between your 2 peaks for calibration. Okay, and then click OK. Okay, so that's a little high. So I'm going to translate my beam a little bit off. That's actually better than moving the stage, I think. I'm going to reduce the size. Okay, too much. Okay, that should be good enough. Okay, there we go. And you can see like I'm nicking the side of the grid here. Looks like somehow we got a little bit off eccentric, but it doesn't really matter a whole. I mean, you want to be close to eccentric. If you're not perfectly there, it's not fine. I mean, in principle, collecting the X-rays, I mean, it's going to affect the efficiency, but it has nothing to do with your energy calibration, of course. So, although I'll go ahead and tweak this once once this detector segment calibration is done. Okay, click OK. Okay, so this one's, I guess, giving a little more shadowing. So I'm going to move the beam over onto the grid a little more. Again, I want to be at the high end of that green region. All right, that's good. I can't go into my office today because they're cleaning the carpets. So I'm here living in the microscope control room. And I thought this is a perfect time to make some videos. So it's very interesting. Like, I guess it's not, it doesn't have to do this like for each dispersion, which is interesting. It's just doing this once and somehow it's applying equally for every dispersion. When we're done, we can go back and we can, do some test acquisitions and make sure that our results are accurate, which is always a good idea to do. Okay. And that's good. Can give it a little bit more juice here. Okay. And there we go. Yeah, so pretty quick to do. It's only 30 seconds a segment. But again, you need a standard, right? To do this. Don't do this with an unknown. So yeah, this is pretty standard for doing EDS calibration is using aluminum and copper. Whether you're on an EDS in SEM or in STEM. Okay. And we're good. Oh, and I forgot to tweak the height, but that's okay. You weren't off by that much. Okay, so again, that has nothing to do with collection of or that has nothing to do with the X-ray energies, right? So may have affected the collection efficiency, but no big deal. All right, so we're nicking the grid here. Let's go to Velox acquisition and let's check. So let's start with 4 kV. We'll put the shaping time as optimized and let's do an exposure here and see. Actually, let me click on this, 60 seconds. We'll just do 15 seconds live time because we can't actually like annotate these. So let's do an acquisition. Yeah, so we can't detect the copper K, but the L is accurate, the O is accurate, the C, everything's good here. So this is looking really good. Okay, so that's done. Let's bump it up to 8 and we'll do the same thing. And again, we still can't get that copper peak there, but these are all still looking good. I wouldn't recommend that you use carbon and oxygen for doing your energy calibration. The reason is that these can be susceptible to slight variations in energy due to what's called chemical shift. So I would not use those for doing your energy axis, your EDS calibrations. I would use um, something that's a little bit higher, in this 1 to 2 keV range. All right, but that looks good. We'll switch it to 20. Yeah, and that's dead on right there. All right, that's done. And let's check 40. It's looking good. If you left click and drag, you can stretch the axis. If you hold down shift, you can shift it without stretching. You scroll wheel, you can shrink your intensity axis. Right click auto scale, that puts it back to the default. Okay, so this is done. And one more to check is the 80. Again, I don't know if I've ever successfully detected an X-ray out this far. Um, but yeah, this is accurate. Looking good. So yeah, the shaping time. So this is basically the the um the time used for the pulse processor to process the pulses and figure out what energy you have. Um, it's best to just leave this at optimized rather than messing with all of these. Um, because it's just a good balance between resolution and throughput. So, but you can do this if you really wanted to, get tighter peaks. So let's try this here. If we put this on high resolution, let's put this back to 20 and let's do an acquisition here. So we should see the dead time increase when we do this. Yeah, so the dead time went up. We can compare this. That's with high resolution. Let's do one with high throughput as well and see if there's any difference in our peak widths. Okay, so that's done. Let's put this at high throughput. We should see the peaks get wider at high throughput. Okay, so that's done. So I'm estimating the full width half max here. Okay, so this window here, that's 165 electron volts. So if we come back to this one, this was the high resolution one. So let's see what we got here. Okay, so that's about, yeah, same. Whoops, whoops. Okay, that's about there. That's about there. Yeah, so the peak width is a little bit smaller. It's about 20 electron volts smaller with the high resolution than it was compared to the high throughput. If we find so this should have been the optimized one. So let's see what that is. Okay, so that's about 9. So we'll be there, be about 4.5. So that is interesting. So this is actually a little bit better than what we were getting here, unless I just measured this wrong, which I suppose that's 165. That's 145. Yeah, so this is actually a little bit, and again, this is an unscientific measurement here, to say the least. Um, yeah, so this is actually very similar in terms of the full width half max, the optimized versus the high resolution. So yeah, so that's just a another reason why probably just use optimized here. Not a huge difference between this and high resolution. I mean, the effect might be a little bit more dramatic actually if you look at these lower energy peaks here. So that's aluminum. Look at the aluminum here. That's 115. That's about the full width half max. 13. So we'll call it about there. Yeah, so here it's definitely, yeah, so it's definitely yeah, the optimized seems to be giving a little bit better resolution. Very interesting. Not so sure about that, but all right, so we just leave it on optimized. But anyways, that's how you do the calibration. The important thing is that the peaks are where they're expected to be. Okay. The fact that we're not exactly seeing the behavior with the peak widths with changing the shaping time, this may need to be adjusted. So I know that there is that can be also done, but that has to be done, I think, at a maintenance level. So that's something that I can't do here. But this is calibrating just the energy axis. So that may be something I need to ask about. So, anyways, that's the other video here. So hope you found that useful, and planning on doing another one here in just a minute. So stay tuned.